Hi everyone, I'm Hanie Sedghi and I'm going to talk about what is being transferred in transfer learning. This is joint work with Behnam Neyshabur and Qian Zhang. One desired capability of machines is to transfer their knowledge or understanding of a domain that it's trained on to another domain where data is scarce or fast speed of convergence is needed. There's a plethora of works using transfer learning in different applications, but we still do not understand what enables a successful transfer and which parts of the network are responsible for that. In this paper, we address these fundamental questions and propose new tools and analysis. Here is a summary of our results. First, both feature reuse and low-level statistics of the data are important. We see that fine-tuned models make similar mistakes on target domain. They have similar features and they're surprisingly close in L2 distance in parameter space. Interestingly, we show that fine-tuned models are in the same basins in the loss landscape, while models trained from random initialization are in a different basin. We see that lower layers are in charge of general features, and higher layers are more sensitive to perturbation of their parameters. We also show that one can start from earlier checkpoints of pre-trained models without losing accuracy of the fine-tuned model. In this short presentation, I'll talk about two of the results, and you could see the rest in our paper. Here's the problem setup. We look into target domains that are intrinsically different and diverse. We look into CheckSpurt, which is a medical imaging data set of chest x-rays considering 5 different diseases. We also look into DomainNet, which is designed to probe transfer learning for diverse visual representations. The domains range from real images to sketches, clip art, and painting samples. There are 345 classes, and you could see the sample of images on the right. We look into 2 initialization scenarios. First, if you pre-train your model on ImageNet and fine-tune it on the target domain, which we refer to it as fine-tuned model, or if the other case is to start from random initialization and we refer to it as RandInit. First, we look into role of feature reuse. Comparing the learning curves, we see that the largest performance boost happens on real domain, which contains natural images, and it's closest to the ImageNet. We also see that even for most distant target domains, such as CheckSpurt and QuickDraw, we still observe performance boosts from transfer learning. We also see that the optimization for fine-tune converges much faster than RandInit in all cases. To investigate this further, we'll do this following experiment. We partition the images of the downstream task into equal-sized blocks and shuffle the blocks randomly. As you could see in the row below, the shuffling disrupts visual features in those images. The details of the experiment are in our paper, and here's the summary of what we see. We see that feature reuse plays a very important role, especially when downstream tasks share similar visual features with the pre-training domain. But we also see that there are other factors at play. Low-level statistics of the data that are not ruined in the shuffling lead to the significant benefits of transfer learning, especially on optimization speed. The other thing we look into are performance barriers and basins in the loss landscape. We know from the literature that any 2 minimizers of a deep network can be connected via a nonlinear low-loss path. We also know that due to the nonlinear and compositional structure of neural networks, linear combination of the weights of 2 good-performing models does not necessarily define a well-behaved model. Thus, we expect performance barriers to exist along this linear interpolation path. On the other hand, we know that when 2 solutions belong to the same flat basin of the loss landscape, performance barrier is absent. And interpolating 2 random solutions from the same basin could generally produce solutions closer to the center of the basin, which potentially have better generalization performance than the endpoints. In the paper, we evaluate a series of models along the linear interpolation of the weights of 2 models. And we see that, as you can see in the plot on the right, fine-tuned models reside in the same flat basin, which you could see in the purple line, which shows the linear interpolation of two fine-tuned models. On the other hand, the blue and red line show if you interpolate a rand init and a fine-tuned model or two rand init models, and you could see the loss barrier. What we see is that rand inits end up in a different basin even if starting from the same random seed. In the paper, we do a lot of experiments and investigate this further, even if you're looking into cross-domain analysis. Our paper is accepted at NeurIPS 2020 and it's available online. Please refer to it for more experiments and more detailed analysis. Thank you.